According to the National Electrical Code Section 450.3 of AIR, a disconnect is generally required on the secondary side of a transformer if it is rated more than 50 kVA and supplies a building or structure. The transformer in question is rated at 480 volts to 208Y/120 volts, which corresponds to a 750 kVA transformer. Because 750 kVA is greater than 50 kVA, a disconnect is required on the secondary side of this transformer, assuming it is supplying a building or structure. Moving on to the primary side, National Electrical Code Section 450.3b outlines the requirements for disconnecting means on the primary side of a transformer. There are a few conditions that trigger this requirement. Firstly, if it is a dry-type transformer rated more than 25 kVA. Secondly, if it is an ungrounded transformer rated more than 600 volts. And thirdly, if it is a grounded transformer rated more than 1000 volts. Given that the transformer in question is a dry-type transformer rated at 480 volts, and its kVA rating exceeds 25 kVA, disconnecting means are indeed required on the primary side. To elaborate on the secondary side disconnect requirements, it's important to consider the purpose of the disconnect. It's there to provide a means of de-energizing the transformer for maintenance, repair, or in emergency situations. The specific type of disconnect will depend on the application and local codes, but it generally needs to be readily accessible and capable of interrupting the full load current of the secondary. The 50 kVA threshold is there to differentiate between smaller transformers where a disconnect might not be as critical for safety and larger transformers where the potential hazards are significantly greater. When determining the kVA rating of a three-phase transformer, the following formula is used: kVA equals volts times amps times the square root of 3 divided by 1000. In this case, with a 480 to 208Y/120 volt transformer, the kVA can be calculated based on either the primary or secondary voltage and current. Since the transformer is rated at 750 kVA, it implies that the primary and secondary currents are sized accordingly to achieve this rating. Concerning the primary side disconnect, the requirement for dry-type transformers rated over 25 kVA stems from the potential fire hazards associated with larger transformers. A primary side disconnect allows for the complete energization of the transformer, which is essential for safe maintenance and troubleshooting. The voltage thresholds for ungrounded and grounded transformers rated over 600 volts and 1000 volts respectively are also related to safety. Higher voltage systems pose a greater risk of electrical shock and arc flash, so disconnecting means are crucial for protecting personnel. When selecting a primary side disconnect, it's important to ensure that it is properly rated for the voltage and current of the primary circuit. It should also have an adequate interrupting capacity to safely clear any potential fault currents. It is also worth noting that the location of the disconnects is also important. They should be readily accessible to qualified personnel and located in a safe place where they can be operated without exposure to hazards. The National Electrical Code provides specific guidelines for the location and accessibility of disconnect. Regarding the 450-foot distance between the 500 amp breaker and the transformer, it's essential to consider voltage drop. The conductors feeding the transformer must be sized appropriately to minimize voltage drop and ensure that the transformer receives the proper voltage. The National Electrical Code Article 310 provides guidance on conductor sizing and voltage drop calculations. A significant voltage drop can lead to reduced performance of the transformer and any equipment connected to its secondary side. In this specific installation, a 500 amp breaker is serving the transformer. The size of the conductors feeding the transformer should be based on the transformer's primary current rating, taking into account any applicable dating factors for ambient temperature or the number of conductors in a raceway. Furthermore, the overcurrent protection for the transformer should comply with National Electrical Code Section 450.3, which specifies the maximum allowable overcurrent protection based on the transformer's kVA rating and primary voltage. The 1000 amp disconnect on the secondary side of the transformer, feeding a 1000 amp distribution panel, suggests that the secondary conductors and overcurrent protection are sized to accommodate a load of up to 1000 amps. It's important to verify that the distribution panel and all connected equipment are properly rated for the available fault currents at the transformer's secondary terminals. A short circuit study may be necessary to determine the available fault current and ensure that the equipment has an adequate interrupting rating. To summarize the key points, firstly, a disconnect is required on the secondary side of the 750 kVA transformer based on National Electrical Code Section 450.3 if because it exceeds 50 kVA and presumably supplies a building or structure. Secondly, a disconnect is also required on the primary side of the transformer based on National Electrical Code Section 450.3b because it is a dry-type transformer rated over 25 kVA. Thirdly, the conductors feeding the transformer should be sized to minimize voltage drop and ensure proper voltage at the transformer's primary terminals. Fourthly, the overcurrent protection for the transformer should comply with National Electrical Code Section 450.3. And fifthly, the secondary conductors, disconnect, and distribution panel should be rated for the available fault current at the transformer's secondary terminals. In addition to these requirements, it's crucial to consult local codes and regulations, as they may impose additional requirements or restrictions on transformer installations. A qualified electrical engineer or electrician should be involved in the design and installation of the transformer to ensure compliance with all applicable codes and standards. Regarding the location of the transformer itself, installing a dry-type transformer outdoors requires consideration of environmental factors. The transformer should be installed in a weatherproof enclosure to protect it from rain, snow, and other environmental elements. The enclosure should also provide adequate ventilation to prevent overheating of the transformer. If the transformer is located in an area accessible to the public, it should be protected from vandalism and unauthorized access. This may involve installing a fence or other barrier around the transformer enclosure. The National Electrical Code provides guidelines for the installation of transformers in various locations, including outdoor installations. It's important to consult these guidelines to ensure that the installation meets all safety requirements. Furthermore, the grounding of the transformer is a critical aspect of the installation. The grounding system should comply with National Electrical Code Article 250, which provides detailed requirements for grounding and bonding electrical systems. Proper grounding helps to minimize the risk of electrical shock and provides a path for fault current to flow back to the source, allowing the overcurrent protection devices to operate correctly. The grounding electrode system should be properly sized and installed to ensure effective grounding. This may involve the use of ground rods, ground rings, or connections to the building's steel structure. In the case of a 480 to 208Y/120 volt transformer, the neutral point of the secondary winding should be grounded to provide a stable reference point for the 120 volt system. This grounding connection should be made at the transformer and at the distribution panel. The size of the grounding conductors should be based on the size of the service entrance conductors, as specified in the National Electrical Code. In addition to grounding, bonding is also essential for electrical safety. Bonding involves connecting all metal enclosures, raceways, and equipment together to create a low impedance path for fault current. This helps to minimize the voltage between different metal parts and reduces the risk of electrical shock. The bonding conductors should be sized appropriately and securely connected to all metal parts. The National Electrical Code provides detailed requirements for bonding electrical systems. It's important to follow these requirements carefully to ensure a safe and reliable electrical installation. When working with transformers, it's crucial to be aware of the potential hazards associated with high voltage and high current. Only qualified personnel should perform installation, maintenance, and repair work on transformers. Proper personal protective equipment, such as gloves, safety glasses, and insulated tools should be used at all times. Lockout/tagout procedures should be followed to ensure that the transformer is de-energized before any work is performed. These procedures involve disconnecting the power supply to the transformer and placing a lock-in tag on the disconnecting means to prevent accidental re-energization. Regular inspections and maintenance of the transformer are essential for ensuring its continued safe and reliable operation. These inspections should include checking for signs of damage, overheating, or corrosion. The transformer's bushings, connections, and cooling system should be inspected regularly. Any problems that are identified should be addressed promptly to prevent further damage or potential safety hazards. In summary, the installation of a 480 to 208 Y/120 volt transformer requires careful consideration of numerous factors, including disconnect requirements, conductor sizing, overcurrent protection, grounding, bonding, and safety procedures. Compliance with the National Electrical Code and local codes is essential for ensuring a safe and reliable electrical installation. Consulting with a qualified electrical engineer or electrician is recommended to ensure that all requirements are met. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical professional for specific recommendations regarding your project. Furthermore, the National Electrical Code is updated regularly, so it's important to stay informed of the latest changes and revisions. This will help to ensure that your electrical installations are always in compliance with the most current safety standards. The use of appropriate software and tools can also aid in the design and analysis of transformer installations. These tools can help to calculate voltage drop, fault current, and other critical parameters. They can also assist in the selection of appropriate conductors, overcurrent protection devices, and other equipment. Many electrical engineers and electricians rely on these tools to streamline the design process and ensure accuracy. In addition to the technical aspects of transformer installations, it's also important to consider the economic aspects. The cost of the transformer, conductors, disconnects, and other equipment can be significant. It's important to carefully evaluate the different options and select the most cost-effective solution that meets all performance and safety requirements. The long-term operating costs of the transformer should also be considered. Energy-efficient transformers can help to reduce energy consumption and lower utility bills. The cost of maintenance and repairs should also be factored into the overall economic analysis. By carefully considering both the technical and economic aspects of transformer installations, it's possible to achieve a balance between performance, safety, and cost-effectiveness. This will help to ensure that the electrical system is both reliable and sustainable. Finally, it's important to remember that electrical safety is paramount. Always prioritize safety when working with electrical equipment. Follow all applicable codes and standards, and use appropriate personal protected equipment. If you are not qualified to perform electrical work, hire a licensed electrician. By taking these precautions, you can help to prevent electrical accidents and ensure a safe working environment. The information presented is based on the National Electrical Code and general engineering practices. Always consult with a qualified professional for specific guidance on your project. They can provide tailored recommendations based on your specific needs and circumstances. It is also worth noting that specific local jurisdictions and utility companies may have additional requirements or interpretations of the National Electrical Code that must be followed. Checking with these entities during the planning and design phase is crucial for a successful project. The National Electrical Code serves as a foundation for safe electrical installations nationwide. However, local amendments can exist due to specific environmental conditions, infrastructure limitations, or historical practices. Understanding and adhering to these local rules is just as important as following the general National Electrical Code guidelines. Beyond code compliance, it is also beneficial to consider future expandability when designing a transformer installation. Planning for increased capacity in the future can save significant costs and disruptions compared to upgrading the system later. This might involve selecting a transformer with a slightly higher kVA rating than currently needed or installing larger conduit to accommodate additional conductors in the future. Taking a proactive approach to future needs can ensure that the electrical system remains adequate and efficient for years to come. When choosing a transformer, it's also important to consider its efficiency rating. Higher efficiency transformers consume less energy, which translates to lower operating costs and reduced environmental impact. Look for transformers that meet or exceed industry standards for energy efficiency. While these transformers may have a higher upfront cost, the long-term savings can often outweigh the initial investment. Regular monitoring of the transformer's performance can also help to identify potential problems early on. Monitoring parameters such as voltage, current, temperature, and oil level can provide valuable insights into the transformer's health. Implementing a preventative maintenance program based on this monitoring data can extend the transformer's lifespan and prevent costly breakdowns. Furthermore, consider the impact of harmonics on the transformer. Nonlinear loads, such as electronic devices and variable frequency drives, can generate harmonic currents that can overload the transformer and reduce its lifespan. If harmonic currents are present, it may be necessary to install harmonic filters or use a K-rated transformer designed to withstand harmonic loads. The selection of appropriate cables and terminations is also crucial for a reliable transformer installation. Cables should be sized to handle the full load current of the transformer, taking into account any limiting factors for ambient temperature and conduit fill. Terminations should be properly installed and torqued to prevent overheating and loose connections. Regular inspection of cables and terminations is essential for identifying and addressing any potential problems. In addition to the electrical aspects of the installation, it's also important to consider the mechanical aspects. The transformer should be securely mounted on a stable platform that could support its weight. The platform should be designed to withstand seismic forces if the transformer is located in an area prone to earthquakes. The transformer should also be protected from physical damage from vehicles or other equipment. Finally, it's important to document the entire transformer installation, including the transformer's specifications, wiring diagrams, and test results. This documentation can be invaluable for troubleshooting problems and performing maintenance in the future. It's also important to keep this documentation up to date as any changes are made to the installation. By following these guidelines, you can help to ensure a safe, reliable, and efficient transformer installation. Remember to always consult with qualified professionals and follow all applicable codes and standards. Electrical safety is everyone's responsibility.